In this complementary material, we want to discuss least action principle for the fields. To simplify the discussion of the least action principle for the gravity, we will consider least action principle for the scalar fields. So to understand, and even more, we will consider two-dimensional scalar fields. But to understand deeper field theory, let us consider the following situation. Let us consider a net of particles, infinite net. So this is, say, indexed, this is number 0, this is -1, this is 1, and so forth to infinity, 2, etc., -2, etc. So we have such a collection of particles, each one of them having mass m, and springs having the Hooke index k. Hooke index k. It is not hard to find that the action for this system, which is just the integral over dt from t1 to t of the Lagrangian, which is just the difference between total kinetic energy minus total potential energy. And in our case, this is just T1, T2, where here total kinetic energy is just the sum of all kinetic energies of the particles from -infinity to +infinity. M phi I dot squared over 2. Who is phi, I will explain in a second. Sum over I from -infinity to +infinity, k phi I plus 1 minus phi I squared over 2. Phi is just displacement. So in equilibrium, particles are positioned at equal dispositions from each other along this line. So, but when we move one of the particles in one or the other direction from its equilibrium, the displacement from the equilibrium we call as phi I, where I is the number of the particle. So the displacement, if we moved one of the particles, they start to shake somehow. There are waves running. So this is we're going to describe these waves with this discussion, which we are going to conduct. So they are changing in time. So that's what we get. Now, it's not hard to see. I assume that listeners of this course, they know the minimal action principle, at least in non-relativistic situation. And minimal action principle in non-relativistic situation leads from this action to the following equation. M phi I double dot is equal to k phi I plus 1 minus phi I minus k phi I minus phi I minus 1. So the meaning of this formula is very simple. It's just a Newton's second law. M times the acceleration of each particle is equal to the force acting on it from one side, from this side, by the spring, which is on the right-hand side, and the force by the spring on the left-hand side. So these are two forces acting on this particle, which are, I mean, the sign can be plus because this could be bigger than this one. Depends on whether the spring is shrinking or expanded. Okay, anyway, now we wanna, what does it have to do with the field theory? Well, let us take the continuum limit. Continuum limit means that we wanna somehow consider on one side, on the physical side, we wanna consider long wavelength fluctuations of this system, such that the wavelengths of the waves which are running along this system are much bigger than the distance between the balls, between the particles. And on the other hand, this is just some analog of a crystal, one-dimensional crystal. And if we look very far at the crystal, it looks completely homogeneous. So we want to discuss this homogeneous situation. What does it mean mathematically? Mathematically, it means that this index I becomes continuous. So it becomes some continuous coordinate x. What does it mean? It means that phi I of t becomes some field phi x t. Well, you see, before taking the continuum limit, the field is just, if we are given phi i's for all the particles, so value of phi for every particle, this collection gives us discrete field at given moment of time. But when we take continuum limit, this guy describes to you kind of displacement or inhomogeneity, compression or expansion of the crystal nearby the point X. I hope it's clear what I mean. So this is a two-dimensional field, 1 plus 1 dimensional field, one space, one time. So then, if this is the case, then Fi plus 1 of t, so to say, goes into Fx plus delta x of t. Then it is not hard to see that Fi plus 1 of t minus Fi of t goes into, as not hard to see, into F prime of x and t times delta x, two linear order in delta x. So what does it do with this? Well, let us multiply this by delta, so divide by delta x here, and multiply. And here we divide by delta x squared, and multiply by delta x hence here, and then we take out delta x. So we didn't do anything. Like if we enter this into the brackets, it cancels with this, and cancels, everything cancels out. Now we want to take delta x going to 0, delta x going to 0, but keeping this ratio and this ratio fixed in this limit, such that m over delta x is fixed constant, m bar, and k times delta x is fixed constant, k bar, in this limit. So what does it mean, keeping these things? We want to obtain an elastic crystal, such that it has some elasticity properties. If we don't fix this constant, then the density in this limit, density goes to infinity. Or the Hooke's coefficient per unit area, per unit length becomes infinite or 0. So if we do not fix this constant, we either in this limit obtain a collection of dust, of particles consisting this crystal which are not interacting to each other, then this is not a crystal, or we obtain absolutely rigid tensor, either that or that. But if we fix this constant fixed, this quantity is fixed, we obtain some elastic body, and that's our goal. Now, what do we obtain in this limit then? Well, this guy becomes phi prime, as one can see, and as a result, this action goes into, let me write it, well, we can write it like this. It's t1, t2, dt, integral over dx. The sum with delta x goes into integral from minus infinity to plus infinity. And we obtain something like this. M bar over 2 phi dot squared, where phi is this field, minus k bar over 2 phi prime squared. Dot means the differentiation with respect to t, and prime means the differentiation with respect to x. So if we write this like this, k bar over 2 dt dx minus t1, t2 minus infinity to plus infinity, here we obtain 1 over c bar squared, phi dot squared, minus phi prime squared. what is C bar? C bar is just M bar over K bar. Sorry, C to the minus first is square root of this. This is some quantity having the dimensionality of velocity. C bar is having dimensionality of velocity, as can be seen from the dimensional properties of this quantity. And it has the meaning of the speed of sound in this crystal. So if we introduce the vector xa, c bar t, and x, where this is x0 and this is x1, then this quantity can be written as follows. K bar over 2. This k actually can be absorbed into rescaling of phi, which is not a problem, dt dx. And here we have dA phi, dA phi. So this is the action for the fields. Simplest two-dimensional field in even having the proper sign here.